they get back, but they didn't do it. So homework 11, it was originally due on Tuesday, which is the same day as the exam. I extended that deadline to Thursday. Not because I think you shouldn't do it before the exam, but just so you have one last thing to worry about on that day. I still highly recommend that you do this assignment before the exam, but again, it won't be due until Thursday. So it's your prerogative, but there will be information on the exam that comes from this homework assignment, so that's up to you. Our exam Tuesday, hopefully you've been studying all along the way, and you're not waiting until Monday night to study for it. But in general, this exam is the easiest exam of the class. So you did well on the first and second exam, you can rest easy, but don't get too overconfident. As one student found out last semester who got a really bad grade on the third exam and thought that he had aced it. He ended up acing the final though, so that worked out for him. Okay, so today we're talking about entropy, and before I even begin this lecture, I just want to say that it's going to be very confusing to you. Not because I'm purposely trying to make it confusing, but this topic is one that even I don't understand really well after studying it for many, many years. I understand the theories behind it, I understand why the math works out, but why entropy is the way it is, I don't know. It's somewhat of a philosophical question as well, but just keep an open mind, recognize that it's going to be different from the way that we've studied other topics previously in the semester, and you can't think about it the same way that you do energy or mass transport or things like that. So with that said, let's start with the second law. So the second law and entropy are related, they go hand in hand. Entropy is another statement of the second law, and the second law helps to prove that entropy exists. And when we studied heat engines, we looked at both the reversible and the irreversible case. So the reversible case was the Carnot heat engine, and we found that its efficiency was greater than that of the irreversible case. Similar with heat pumps and refrigerators, the coefficient of performance for a reversible heat pump or refrigerator is greater than that for an irreversible one. So we have these inequalities which lead us to believe that there's something about the reversible case that is different. Okay, there's some factors that go into it. Yes, we understand, it's more efficient or it works better, but why? And what are these efficiencies taking away from the system that cause it to be a reversible heat engine to be better than one that's not irreversible? Which brings us to something called the Clausius inequality. We're going to go through how this inequality comes about mathematically a little bit later, but this is considered the Clausius inequality. And it says that for a cycle, if you integrate over a cycle, that's what that integral with the little circle means, that if you take all the differential amounts of heat transfer and divide them through by the temperature at which that heat transfer occurs, it's always going to be less than or equal to 0. Okay, we'll talk about this later and explain it. So in the case of an internally reversible cycle, or a system which is internally reversible operating on a cycle, we find that the equality holds true, which means that for an irreversible case, this del Q over T must be less than 0. Okay, so for the reversible case, it's equal to 0. For the irreversible case, it's less than 0. We're going to look at that in just a second. So let's just imagine that we have two devices. One is what? What does that look like to you? Okay, a heat engine. How do you know it's a heat engine and not a heat pump? Okay, so there's some network output on this reversible cyclic device. In this case, we're assuming it's operating as a heat engine, so there's some network output, and there's a heat addition from QR, or del QR at TR, and then there's some heat rejection, del Q. We're going to assume that this heat rejection goes straight into another system, which allows it to have some network out or in. Okay, so we're not powering, but adding heat to this additional system with our rejection process from this heat engine. Okay, so this is an imaginary system. If you look at the system boundary right away, what do you notice?
Yeah, two work out, no work in.
Okay, there's no work in, there's a heat in, but there's work out. Okay, so would this be possible in real life? No. Okay, so this combined system is theoretical, and we're going to use it to prove the Clausius inequality. So if we apply the energy balance to this system, we have some net work of the combined system, this del work out, is equal to this Q in minus the change in energy of this combined cycle. So we've kind of rearranged that. It would be D E is equal to del work minus del Q. If it's a reversible cycle, then this del QR over TR is just equal to del Q over T. We're just going to call it that. If we want to solve for this del QR or this del Q over T and we substitute, then we say that the combined work of this cycle is equal to this del Q over T multiplied by TR. So we've just substituted in this del QR is equal to TR times del Q over T. We've just substituted that in there, minus the change in energy of this combined system. And if we integrate over a cycle to get the total work, then the work of this combined system is equal to TR times the cyclical integral of this del Q over T. Okay, so right now we're just playing around with the math using this combined cycle to come up with something that's useful to us. Okay, the reason this DEC goes away is why? Do you know? Okay, if it's integrating over a cycle, the change in energy of this combined system should be 0. It should return back to its initial state. So that's how that disappears or goes away. Okay, so all we've done is just take the energy balance on this combined system that's theoretical, and we've already seen that it can't possibly happen, and then we integrate over a cycle. So I'm just we're just playing around with the terms in it. Okay, so if this is a network output, this would be an impossible cycle, right? Because we have heat coming in from a single reservoir and then having some network output. That's not possible. It violates Clausius, violates self-plane. Okay, so we know that this term on this side of the equation has to be negative, has to be less than or equal to 0, meaning that we can't operate in this manner with a network output. So in reality, it's like we have a negative work output, or in other words, a work input. Okay, so that's why this term has to be less than or equal to 0 for any cycle. For a reversible cycle, it will be equal to 0. For an irreversible cycle, it will be less than 0. So if you integrate over an entire cycle, del Q over T has to be negative. Okay, so when we talk about a cycle, at the end of a cycle, all the properties must return to their initial state. So enthalpy, internal energy, volume, they would all return back to their initial state. And we also have another property now that we're learning about called entropy. So at the end of a cycle, the entropy also will return to its initial state. Okay, so if we integrate this del Q over a cycle and it's equal to 0 for an internally reversible process, we say that the entropy, ds, is equal to this del Q over T. So we're now saying that the integral of this over an internally reversible cycle is the entropy. Okay, so the entropy change, S2 minus S1, from state 1 to state 2 is going to be the integral of del Q over T. Okay, so that's how we're defining entropy. So we've determined from the Clausius inequality that there's this ratio, the integral of del Q over T, and we're now going to call that entropy. Okay, we've kind of come up with a new property value based on this math that we've done. Okay, again, I can follow the math. I can understand the math. Why they decided that this is now entropy and that we always have an increase of entropy, it's, I understand that too, but then at the same time, I think who came up with this and why. Anyway. Okay. So again, entropy is just like a property value. So it's dependent on two independent properties at a given state. We can look it up in the table. So if you look in the back of your book where we have internal energy and enthalpy and specific volume, on the far right of that column, there's also entropy. We haven't used it up until now, but it's there in the tables, and you look it up the same that you do any other property value. Okay, so what is it? Well, it's useful to us when we perform our second law analysis, because we can assume that if a process is to occur in real life, later we'll learn that the entropy has to increase. Okay, the entropy of the system might decrease, but the entropy of the surroundings would have to increase by at least as much. So it's useful in determining whether or not a process is real, because if it doesn't satisfy this increase of entropy principle, as we'll talk about later, then it can't happen. Okay. So it's another way to put it to the test to see if the second law holds true. We can also consider entropy to be like molecular disorder or randomness. And when we look at gases, they're in a very high energy state. So they're useful to us in terms of availability to provide energy. But because they're so disorganized and random, sometimes it's difficult to harness that energy or to use it in a way that provides value to us. So sometimes substances that are in a high energy state also have a high entropy state. And so the release of entropy into the environment when we use these high energy materials for our system is sometimes greater than if we were to use the lower energy state materials. Okay. And again, we'll get a little bit more into this. I think chapter 7 is probably the longest chapter in the book, and we spent several weeks on it. So this is sort of just the introduction to the concept. And then we come about the third law of thermodynamics, which says that the entropy at absolute zero is zero. The reason that it is zero is because the molecules stop moving. So we can predict with 100% accuracy where those molecules are at any given point in space or point in time when it's at absolute zero. Okay, so there's no disorder, there's no randomness to the position of the molecules, because even in the solid state, the molecules are oscillating slightly around their point. Okay, we don't often look at molecules individually unless we're doing statistical thermodynamics, but that's the definition of the 0 point of entropy is when all molecular motion ceases at absolute zero. Okay. And then that's the third law of thermodynamics. Okay, so if we look at energy, even though it's a high, if it's in a high energy state, like a gaseous state, it's somewhat disorganized. Okay, so if we were to just put a shaft into some chamber that has gas in it, and these molecules are bouncing all around, they really have a lot of energy associated with them, but they don't combine together to start turning that paddle wheel for us. We have to harness them in some way or channel them in some way in order to provide useful work output. And as this energy quality degrades, so as we go from a gas to a liquid to a solid, there is some production of entropy in that process. So as we go from high energy, high quality, like electrical work, to heat, there's a production of entropy in that process. So as the energy quality goes into a less quality form, then entropy is released into the surroundings, is created. Okay? And real processes will occur in the direction of increasing entropy. Okay, so a hot body to a cold body, the entropy in the surroundings will increase. Okay, the entropy of this hot body is decreasing while the entropy of the cold body is increasing. Okay, so although the potato may lose some entropy, the surroundings gain that entropy. So it's going from a state of high entropy in the potato to a state of high entropy in the surroundings. So entropy is released from the potato into the surroundings.
So yes. Entropy like the inverse of enthalpy? Is that what you're saying? It's basically putting a numerical value on it?
It's putting a numerical value on the randomness of the material. It's not the opposite of enthalpy, but it sometimes works counter to enthalpy. I guess as the material is more random and high energy, it's more difficult to get useful work from it, but there's more useful work available. So enthalpy will be higher at a higher temperature, so will entropy, but it's sometimes difficult to get that enthalpy and use it in a useful manner if it's not organized. Yes?
So entropy is like measured relative to the absolute zero thing. whereas enthalpy is dependent upon like the properties of like a fluid, for example. Or something like that.
Well, the tables that we have some reference point, and as entropy is tabulated in these tables, it depends on whatever reference point is used to calculate the enthalpy. So they'll have the same reference point in the same table. That can vary from table to table to table. And we'll use enthalpy relative to absolute zero as we deal with calculating entropy of ideal gases later, but that's later. Getting ahead of ourselves. Did that answer your question?
Yeah.
Okay. Yeah, so if they're in the same table, they're relative to the same initial point. But sometimes from table to table, depending on how the tables are developed, it might be different. Okay. Are you guys confused yet? Okay, entropy is a very abstract concept. You can't measure it. You can only calculate it based on the formulas or the equations for different substances or properties. Okay, you can look it up in tables, but you can't measure entropy. Yes?
It's really just a way to describe why your calculations are inaccurate. It's just a gap.
Wait. So if you can't prove it, then how do you know it?
You can prove it.
Oh.
You can't measure it.
So if you were like in the lab, you can't say this is what entropy is.
There's no entropy measurement device.
So
You can calculate it, but you can't measure it.
So how do they even come up with the equations to calculate it if they could know?
It's sort of like the leftovers. So this inequality, started showing up in processes that they were analyzing or systems they were analyzing. That this inequality shows up, or this term del Q over T. And when they integrated, they said, well, this is a new property. It's called entropy. What we're actually finding is that this is a measure of the irreversibility of our processes. So
it's just a way to make your equations work by saying some area is actually.
Yeah, I don't care for entropy too much. I don't think.
Not to make the numbers work. It's kind of
right,
little bits of process happen.
right. And there's different uses for it. So it may be accounting for the irreversibilities in the process. So if you're trying to determine where all of your energy has gone, like if you wanted to say this molecule or this group of molecules has a certain energy state, but I'm only able to get out this much energy from it in a useful form, well, that's because there's entropy and disorganization and chaos that happens when I change it from
So
this one to
entropy
another.
is the reason for the thermal efficiency? Is that what you said?
No.
Okay. Well, look,
Entropy is a result of processes that have inefficiencies, we will say.
thermal inefficiency, or what? I mean, the inefficiency of the. Okay, I'm gonna leave it alone. Obviously, and continue to try to put the pieces together.
Yeah, really.
So if you said that it was resulted from that inequality, like that just kept showing up, then how were they analyzing it? I mean, how's it pertinent? Like, I mean, where does it come in if it was something that was discovered after the use of this system that's discovered?
I don't know that it was like much after. It's as all of these equations, first, second law, third law, zeroth law, were coming about. It was sort of in the same general time period, over a period of maybe less than 100 years that people were trying to figure out how to analyze systems, how to determine what the inefficiencies are, where they come from. So it all came about together. So it wasn't that they were looking at systems and applying all of these, equations to define them for a long time, and then somebody was like, hey, let's call this part entropy. It evolved and it came about as they grew a greater understanding of how the processes worked and what the results were. So again.
So entropy is kind of like the percent error.
No.
Okay.
Entropy, wait, sorry.
Does it follow the same direction as heat but measured the opposite way?
Yes. but it depends on your reference point too, so, okay, we'll move on. And as we start applying it, it starts to make a little bit more sense. But again, it's not going to make total sense to you. And just accept that fact that you may not fully understand where it comes from, why it's used, who developed it. But as you look at the application of it, the important thing to remember is that it's a measure of disorder and that it's always increasing. in the universe. So even if the entropy of your system decreases, it causes an increase in the entropy of the surroundings by an equal to or greater amount. Okay, that's the big thing you need to remember about it. Okay, so there's special cases where we can apply this. If it's an isothermal, what does isothermal mean? Constant temperature, internally reversible process, so the system itself can be returned to its original state. Then we can take this temperature outside the integral and we just have 1 over T times the integral of del Q, which just reduces to Q over T. So the change in entropy for an isothermal system that is internally reversible is just Q divided by T. So the amount of heat transfer divided by the temperature at which the heat transfer occurs. So heat transferred to the system will increase entropy, and heat transfer removed from the system decreases the entropy.
So entropy isn't an actual value, it's just exchange of entropy.
Entropy is a value.
Oh, okay.
You can't measure it, you can only calculate it. Okay. So think about this physically, that if you're adding heat to a gas, what happens, or to a substance, maybe it's in a liquid form, what eventually happens? It evaporates, the molecules are moving around, they have higher energy, so the entropy will increase. Similarly, if you remove heat from it and it condenses, it's in a lower energy state and there's less entropy. Okay. So similar to heat, a system doesn't possess heat. We only recognize the amount of heat that's transferred from one system to another. Entropy operates in a similar manner, that a system doesn't possess entropy. You can't measure the amount of entropy, just like you can't measure the amount of heat, but we recognize the entropy transfer as entropy is transferred from one system to another. So let's do an example. So in this problem, we have a piston cylinder device that has liquid vapor mixture of water at 300 Kelvin. And during a constant pressure process, 750 kilojoules of heat is transferred to the water. As a result, part of the liquid in the cylinder vaporizes. We want to determine the entropy change of the water during this process. Okay, so if this, what type of process is this? I guess, what type of system is it? Okay, it's a closed system. How do you know it's a closed system? Okay. No mass transfer. Okay, that's why it's a closed system. It's also a constant pressure and a constant temperature process. Okay, so on the previous slide, we determined that delta S is equal to Q over T. So in this case, we have Q coming into the system. So Q is a positive value of 750 kilojoules. And because this is a constant temperature process, it's happening at a constant temperature, we just divide through by 300 Kelvin is equal to 2.5 kilojoules per Kelvin. So this is an increase in the entropy of this system, delta S, equal to 2.5 kilojoules per Kelvin. What would happen if the entropy was being transferred the opposite direction? Or the heat being transferred the opposite direction? Okay, so we have delta S is equal to Q over T, but in this case, our Q is a negative 750 kilojoules because it's a Q out divided by 300 Kelvin. So we'd have a negative 2.5 kilojoules per Kelvin.
I have a question. Earlier you said that the entropy of the system can increase at a greater amount than what was lost, or the environment can increase
Yes.
it. How is that?
We'll talk about that later. It's called entropy generation. Okay, so because heat is being transferred to the system, it's a positive quantity. If heat were being removed, then the entropy of the system is decreasing. It would be a negative quantity. What would happen if this temperature was not constant? Okay, we would have to integrate using that integral up there. So del Q over T. We would need to know the relationship somehow between heat transfer and temperature and then perform the integration. But because it's isothermal, the temperature is constant, we can do this. The temperature is not constant, you can't apply this equation. You have to go with the beginning one. Okay, let's do another one. Air is compressed by a 30 kilowatt compressor from P1 to P2. The air temperature is maintained constant at 25 Celsius during this process as a result of heat transfer to the surroundings at 17 Celsius. Determine the rate of entropy change in the air. State the assumptions made in solving this problem. Okay, so what are some of the assumptions that we can make? Okay, steady flow. What else? Say that again. Isothermal. What else?
What's flow rate is constant?
Yeah, that's sort of implied in steady flow. What's our working fluid?
Air. Oh, yeah.
Okay, air is an ideal gas. Okay, anything else? Okay, so let's perform an energy balance. Q dot in minus Q dot out plus work dot in minus work dot out is equal to m dot times H2 minus H1, assuming that H1 is the inlet and H2 is the outlet. So in this problem, do we have heat transfer?
Oh, yeah.
Okay, in order to maintain the temperature at a constant temperature, there would have to be some heat transfer, and heat is being, on the picture, it shows removed.
Has to be local. The
Yep.
work being put in.
Right. Q out, so we have work in,
Yes.
we have work out. Okay. How do we find the enthalpy?
It's an ideal gas.
Okay, it's an ideal gas.
We know it's air.
We know it's air.
So then from there, you use the temperature and you just go to the same.
Okay, so we can go to the tables and look it up.
Need pressure.
Do we?
I want to ask.
Okay, for an ideal gas, what is enthalpy a function of temperature? And temperature only, right? So we could rewrite that as m dot C sub P times T2 minus T1. What would this be? T2 minus T1? 0. Okay, so this side of the equation actually goes to 0 because enthalpy is a function of temperature only for an ideal gas. If we're maintaining a constant temperature, then it goes to 0, which means that we have this negative Q out is equal to Q out is equal to work in. So negative Q out plus work in equals 0, or Q out equals work in. And put the dots above those so it's in the rate form. Okay, so if Q dot out is equal to work dot in, then we know our Q dot out is equal to the 30 kilowatts that we put into our system through the shaft. Which makes sense physically because if we're adding this amount of energy to the system and we want the system to have a constant temperature, then we would have to remove the same amount of energy from the system. Okay, so physically it should make sense to us. It's 30 kilowatts. Now we can apply our change in entropy. Delta S is equal to Q over T. And is heat leaving or entering our system? Okay, heat is leaving our system, so we have a negative 30 kilowatts divided by the temperature at which it occurs, which is 298 Kelvin. So we have a negative 0.101 kilowatt per Kelvin.
So what was the point of talking about the surrounding temperature? Was that just kind of?
It's just a red herring. Okay, or we can use it. Let's see. If we wanted to determine the entropy change of the surroundings, then let's do that. So delta S of the surroundings will be equal to Q over T. And in this case, it's 30 kilowatts going into the surroundings, so it would be 30 kilowatts divided by the temperature of the surroundings, which is 17 plus 273, which is 290. I don't trust my math when I'm standing here. Yep. Okay. So 30 kilowatts over 290, what is that? 0.1 what?
103.
03 kilowatts per Kelvin. Okay, so the system decreased by 0.101, but the surroundings increased by 0.103. Interesting. Interesting. We'll talk about that in a minute. Okay. This leads us to the discussion of the increase of entropy principle. Okay, so from the Clausius inequality, we know that this del Q, the cyclical integral of del Q over T, has to be less than or equal to 0. So let's just consider a cycle made up of two processes. The first one is arbitrary, so it can be reversible or irreversible. And the second one is a reversible process. So if we add those two together, so our cycle consists of from 1 to 2, we have a reversible process, and from 2 to 1, no, 1 to 2 is reversible or irreversible, and then 2 to 1 is internally reversible. So we're going this direction. See, the arrow is pointing out. Okay, so from 1 to 2, it's del Q over T, and from 2 to 1, it's del Q over T of a reversible cycle. And we'll say adding those two together makes the entire cycle, so it has to be less than or equal to 0. Okay, so this is our internally reversible process. We can rewrite this one as S1 minus S2. Okay, so if we're going from 2 to 1, then it's S2, or S1 minus S2, gives us the change in entropy for that cycle. Okay, so all we've done is just replace this with a delta S term. We've done the integral. Now if we rearrange these two terms, we have S2 minus S1 is always going to be greater than or equal to this integral from 1 to 2 of del Q over T. Okay, so if 1 to 2 is a reversible cycle, then S2 minus S1 will be equal to S1 minus S2. And if it's an irreversible cycle, then it's going to be greater than. Okay, so for an irreversible process, the change in entropy is greater than the entropy transferred between those two. So there's always some entropy created or generated during a process. So the change in our entropy of the system is equal to S2 minus S1, but it's equal to this del Q over T plus some other term. Okay, so we have entropy generated during any irreversible process. And it's a property of the process itself that determines how much entropy is generated. Okay, so imagine that we're performing some process on the system, and in one case, we do it with minimal inefficiencies. So we try to eliminate friction, we try to eliminate any headlocks, we try to eliminate any like non-quasi-equilibrium oscillations within the system that reduce our efficiency. Okay, as we try to minimize those inefficiencies, we're minimizing the amount of entropy that's generated during the process. As we have greater inefficiencies in our process, then this entropy generation term increases. Okay, so a system can go from state 1 to state 2 in many different ways, and this change in entropy is always going to be the same. because it's a property value. You can look it up in the tables, S2 minus S1 at a beginning and an end point is always going to be the same. But the amount of entropy generated will change depending on the process that you use to go between S1 and S2. Any questions on that? Yes.
Anytime the system is hotter than the surroundings, then the entropy, there'll be entropy generated. That makes this, you divide it by a smaller number, so it gives you a bigger number.
Well, if the entropy, yeah. So if the surroundings were bigger than or hotter than the system, then the flow is from the heat transfer would be from the system, from the surroundings to the system, and so your entropy of your system would be increasing, and it would be increasing by a greater amount than the surroundings lost.
So the bigger the temperature difference and the bigger the between the two, is that basically where it's at?
Depends on how much heat is being transferred. So it's not just the temperature difference, but also how well insulated it might be to prevent heat losses, things like that. So it's a combination of the heat transfer plus the temperature difference at which it occurs will determine how much entropy is generated during that heat transfer process. If it's an isolated system, so in other words, it's a closed system that has no mass flow and there's no heat transfer in between the system, the change in entropy is always positive. So if it's a system that is like there's no heat transfer between it and the surroundings, and there's no mass flowing in and out, the entropy generation is always going to be greater than zero. And it will be zero if nothing is happening. It will be positive if anything else happens to that system. And then entropy generation is always a positive term. You can't have a negative entropy generation. It's always created and it's never destroyed, which means that the entropy of the universe is increasing, okay, which has plagued philosophers for years. If you've ever heard of the term the heat death of the universe, like the universe is always heating up, getting hotter, but eventually it'll be so hot that life doesn't survive or sustain itself. Okay, that's like billions of years off in the future, but
that means energy is being created from nowhere, though, right?
no,
If the universe is getting hotter.
it's just energy is degrading.
So the available energy level is increasing. The high quality energy in the earth is.
The high quality energy of the earth is decreasing, and the result is heat. Okay, so energy is not being created, energy is not being destroyed, it's changing forms. And you're going from a high quality to a low quality. That's the natural direction of the process. And when you try to convert from a low quality back to a high quality, you can only convert part of it back.
So how does that play into the whole, the Earth's on this big cycle of like extremely cold and extremely hot?
Yeah, is that why we have ice ages?
No,
Oh,
that doesn't factor into it. That's more like weather conditions and patterns. Global warming is a result of heat being trapped in the atmosphere, but on the like universal scale, looking outside of us, the low temperature of space is such that if we didn't have the greenhouse gases, then we would be cooling off in amount to that. So I don't think entropy is causing the global warming as we may see it. That's environmental pollution and other factors, but long term, like billions of years long term, then yeah, the heat of the temperature of everything would be increasing.
I just mean like if the temperature is constantly increasing, how do you have periods of decreasing atmospheric temperature on a large scale? Like
Because we're radiating heat to the universe. So that's how it can ever decrease. But overall, the trend of the entire universe in conjunction with all the other planets, all the other star systems, everything else is increasing.
They think in billions of years we're going to be able to increase the temperature of space that much.
I hope I won't be around by then. So this, I mean, yes, this is something that philosophers have thought about and worried about, but it's also something that is so far off in the distant future that it's not going to affect.
But we need to find a solution now before it's too late.
Before yeah. There are more pressing problems that contribute to the increase of entropy, but we can do our best to minimize inefficiencies to slow down the heat death of the universe. Yes. Okay, so it all goes back to the fact that anytime you have inefficiencies in your process, it results in what? Heat. Okay. Okay, so let's do another example. Let's imagine that we want to violate the second law. And in one case, we have heat being transferred from a hot reservoir to a cold reservoir, which is feasible, possible, it can happen. In the other case, we have heat being transferred from a cold reservoir to a hot reservoir. There's no heat engine, we're just making it somehow go there. So let's see if we violate the increase of entropy principle. At a glance, you should look at this and know that yes, we are going to violate the increase of entropy principle. Okay, so the total change in the entropy of our system plus our surroundings is going to be the change in entropy of the source plus the change in entropy of the sink. Okay, so if we look at our system as the 1500 K and our surroundings as the 300 K, then that would be the change in the entropy of everything, system plus surroundings, is equal to our total entropy change. And in order to not violate the increase of entropy principle, this needs to be a positive value. Okay, if we look at the system and the surroundings, it should be positive. So the change in entropy of our source is going to be Q over the temperature of the source, and we're going to say temperature of the source is our TH, plus QH over TH plus QL over TL. We can write it different ways. Okay, so what is our QH? Okay, it's 200 kilojoules, and is it entering or leaving? So it's a negative 200 kilojoules leaving our source at a temperature of 1500 Kelvin. Plus QL is entering our sink. What's the 200 kilojoules. It's positive because it's going into the system at 300 Kelvin. Okay, so if we calculate those, we get 0.533 kilojoules per Kelvin. Okay, so this value is going to be a negative 0.1333 kilojoules per Kelvin. And this value is 0.667 kilojoules per Kelvin. Okay, so the source is decreasing, the entropy of the source is decreasing by negative 0.133, and the surroundings or the sink are increasing by 0.667. Okay, so yes, we have satisfied the increase of entropy principle because overall the entropy increased. So let's see if we perform it in the opposite direction. In this case, we have our QL over TL plus QH over TH is equal to, okay, same amount of heat is being transferred, 200 kilojoules. And is it entering or leaving our sink? Okay, so it's a negative 200 kilojoules, and the temperature at which it's leaving is 300 Kelvin. And it's entering our source, which is now our sink. 200 kilojoules enters at 1500 Kelvin. So we have negative 0.533 kilojoules per Kelvin. Okay, so our entropy in this case is decreasing, which means it does not satisfy the increase of entropy principle. Okay, so this is another way to check if a process violates the second law. So if entropy generation is a positive value, then yes, thumbs up. Okay, it didn't violate the second law. It still might violate the first law. We have to check that too. It could be a real process, but if our entropy generation is negative, then we know that it violates the second law and it's not a real process. It can't happen.
Can we travel back in time real quick?
Yeah.
So, just to clarify, the reason that the loss of the system is not equal to the gain of surroundings, is it because we don't know?
No, it's because there's some irreversibility associated with the process. So in the irreversibility associated with this process is that we're transferring heat from a high temperature and high energy state to a low temperature and a low energy state.
No, I get the difference between these two. Like a couple problems you had.
Yeah.
Remember when you asked why we were given the temperature surroundings, you said right hand, but let's check it out anyway. And the two numbers weren't equal, like the system lost X and the surroundings gained Y, which wasn't equal to X or more. How?
So that's what I'm trying to explain.
Oh, okay, so.
Okay, so it's irreversible because we're starting at a high quality source or high energy source, and we're degrading the quality of that energy. We can't reverse the direction and have it go back to that high quality energy without putting in work. So the entropy generation comes about because we've taken high quality energy, we've reduced it to a lower quality energy, and we can't go back.
Oh,
So we lost some of our quality in the process.
So that previous problem you just proven that had 100% efficiency, but that's not possible. That's why I had that negative number.
If this were,
I was not talking about this one. You see how that first part we had a negative number? You just were proving that it can't be 100% efficiency when you put in the work and all the heat makes it back.
no, that one could be, because it was work going in, going out, and it was leaving as heat.
But we got a negative change in entropy.
The entropy of the system can change and be a negative value.
Oh, so
But when we looked at the entropy of the system plus the entropy of the surroundings, it was a positive value. So the surroundings changed more than the system. And that's because, again, we're taking a higher quality energy like work and converting it to heat. And we can't go back. We can't reverse the process. So the higher the entropy generation, the more irreversible the process is.
The quality factor.
And quality in the terms of the quality of energy, not X quality. Okay, so it's not that we don't know where it comes from or why it happens.
We just can't explain quantity.
You just can't measure. You can calculate it, and it's a measure of irreversibility, but it's not something that you can just, I'm going to see how much entropy is being generated in this room. You can't measure it.
So in calculation, how, one problem now is different, the numbers are different. Is it like an exponential calculation? I mean, how it gains?
Yes.
What do you mean? Like as the temperature changes would be an exponential increase?
No, like the entropy value, it came out to be different compared to like the system and surroundings. And that one question we did that we've been talking about is a calculation.
This one?
So yeah.
Okay.
We calculated the entropy going from the system and then the entropy of the surroundings. And there were different numbers. And you're talking about, I guess, due to the irreversibility of the system.
Uh-huh.
Is it an exponential calculation?
No. I mean, it's a 1/t calculation, but
But you said we'd have to know the value or some relationship of Q to do that calculation, right?
if the temperature wasn't constant, then you have to know the relationship between Q and T in order to calculate this integral. The problems that we've been doing since we talked about this have all had a constant temperature. So if the temperature of the sink and the source were changing, we would have to know the relationship between Q and T in order to calculate this integral. So, if Q is an exponential function of T somehow, then it would be an exponential. But if it's a lot, like a linear function of T or whatever, then it would change how we calculate that integral. But for isothermal problems, the relationship is 1/t. And so it's, the relationship, if you were to calculate as the temperature of the surroundings decreases, then it's not going to be a linear relationship between temperature and Q. It's going to be a 1/t relationship. But,
And then if you integrated that, that would be the natural law.
well, you wouldn't integrate it because it's constant temperature.
Okay.
Is that? I think we're confusing the issue. So we've been doing the special case of this equation. So delta S equals the integral of del Q over T. But in a special case, when T is constant, it comes outside the integral. Any other time, we have to know the functional relationship between Q and T in order to calculate that integral. Any other questions on that? Did that answer your question, or are you still confused?
How it comes up.
You don't understand why
I mean, I am just as slowed up thinking maybe it was an exponential, like maybe it was an exponential gain, some sort of mental law or something.
Yeah, and again, that would just depend on the functional relationship between Q and T. In this case, it's Q over T. It's a 1 over T relationship, so that's how it varies. But yeah, if it's not an isothermal problem, then it's some other relationship.
This stuff will be on our exam.
Yeah, but it's going to be stuff like this kind of a problem where I'm not guaranteeing that, but it's going to be more conceptual and testing your understanding of what is entropy, what does it represent, and how would you figure out whether something satisfies or doesn't satisfy this increase in entropy principle. So I'm not going to give you a functional relationship between Q and T and how you figure out the integration, and I may do that on the final, I don't know, but because we're just talking about this and because I fully understand that this subject is confusing, and it's very different from how we look at energy. Because in energy, you can't create energy. You can't generate it. You can change forms. But with entropy, you can generate it. You can bring it out of nowhere because you have to perform a process, but it's always increasing. There's always some entropy created during the process. And I guess the important thing to remember is that entropy is not a physical thing that you can see or look at it or hold. You see the influence of it in the environment, in the degradation of quality of energy, or in the increase of randomness and disorganization. So you kind of have to think in more abstract terms because it's not a concrete something we can feel. You know, we can experience heat, we can see volume changes, we can hold a mass in our hands. We can't experience really entropy physically. I mean, we do every day, but we don't know that we're experiencing it. Okay. So for entropy generation, if we say that a system is a system plus its surroundings, so if we're looking at a system and its surroundings, the entropy generation always has to be greater than or equal to 0. So the universe, which is all of the systems and all of the surroundings combined into one, can be considered an isolated system. And yes, the entropy of the universe is always increasing. So again, just important to note that an individual system can have a decrease in entropy, but the entropy of its surroundings will increase by an amount equal to or greater than the amount. So if the entropy generation is 0, meaning that the entropy of the system decreases or increases by the exact same amount as the entropy of the surroundings, then it's a reversible process. So there's no irreversibilities that are adding to the entropy of the universe. Okay, so there's no friction that causes heat, and there's no head loss. Okay, but it can never be negative. You can never destroy entropy. So it can be 0 for a reversible process, or greater than 0 for all real processes, but it can never be 0. It can never be less than 0, negative. Okay, let's do another example. A heat source at 800 Kelvin loses 2,000 kilojoules of heat to a sink at either 500 Kelvin or 750 Kelvin. So let's determine which heat transfer process is more irreversible. So which one has the greater entropy generation? Okay, so if we want to determine the entropy generation, we have to look at our system and the surroundings. So we're going to assume the system is the source and the surroundings is the sink. Okay, so I don't need to draw that picture, it's already in there. Okay, so the entropy generation in A is equal to the change in entropy of the source plus the change in entropy of the sink. So the change in entropy of our source is what? Okay, negative 2,000 kilojoules divided by, what is our temperature at which it's occurring? 800 Kelvin. plus we have 2,000 kilojoules going into our sink at a temperature of 500 Kelvin. So the entropy generation for part A is negative 2.5 plus 4 kilojoules per Kelvin. So negative 2.5 here, 4 for the sink is 1.5 kilojoules per Kelvin. For part B, the first part is the same. We have 2,000 kilojoules leaving our source at 800 Kelvin and 2,000 kilojoules entering our sink, but instead of at 500 Kelvin, it's at 750 Kelvin. Now, before I do this math, which one do you think is going to be more irreversible?
A,
Why?
the lower temperature you're dividing by.
Okay, well, not thinking about it mathematically and numbers, why? Physically, why would you think it would be more irreversible?
Because energy tends to go from a high energy source to a low energy source.
Okay.
And it's traveling a greater distance. And the more lower, like you were saying, the more low, it's a lot harder to convert a low energy source to a high energy source. And delta S is a measure of reversibility. So.
Okay, so it's more irreversible because it's further away from where it started. It's at a lower energy state than it started at. Okay, so we would expect that it should be the case when it goes to 500K. So we put in for this, it's negative 2.5 plus 2.6667 kilojoules per Kelvin is 0.1667 kilojoules per Kelvin. Okay, so as we would expect, it's less irreversible to transfer to a temperature that's closer to our original temperature. Okay, so there's less loss associated with it. Okay, any questions on this? So again, we can only apply this when it is an isothermal case or when the temperature of the source or the temperature of the surroundings are constant. So it occurs at a constant temperature. Okay, additional remarks about entropy. As we said during our study of the second law, that processes can't occur in any direction that they want to. It's governed by the second law. And a process has to occur in the direction that complies with the entropy generation principle. So in other words, entropy generation has to be positive or equal to 0 for a reversible case. Okay, so if a process is to occur in real life, not just on paper, it needs to satisfy that principle. Okay, so it's another statement of the second law that there's a directional quality to our energy transfer. It's also not a conserved property. So when we think about energy, energy in minus energy out equals energy change. Well, for entropy, it's entropy in minus entropy out plus the entropy generated is equal to the total entropy change. And that value always has to be positive when you consider the system plus the surroundings. If it's an ideal reversible process, it will be 0, but everything else has to have a positive net entropy change when you consider the system and the surroundings. Or entropy generation has to be greater than 0. And entropy is of concern to us because the more inefficient our systems are, the less usable work we get out of them. So we want to study irreversibilities in entropy to know whether or not our process is as close to ideal as it can be. So anytime we're generating entropy, then we have a process that has inefficiencies associated with it, irreversibilities associated with it, and we want to try to minimize that. Okay, so although entropy is this abstract concept that we can't measure, it's something that is incredibly useful because it's another benchmark against which to test our processes to see if we're doing the best that we can in order to decrease inefficiencies or increase the efficiency of the system. Okay, so we can measure the efficiency, but we can also calculate how much entropy is generated during that process, and that's another means that we can seek to find ways to improve the system. Okay. And it's also another way that we can compare one system to another. So it may be a more efficient system, but if we compare it to another system that has less entropy generation, possibly that's the system we want to go with. So, again, entropy is a property value, and just like any other property value, we can look it up at fixed states. The same relationships exist as they did for other property values, where entropy is equal to, under the dome, if it's a saturated mixture, entropy is equal to SF plus X SFG. So we would treat it the same way we would any other property to look it up and calculate entropy values. Under the dome, you can see that there needs to be two independent intensive properties. So temperature and pressure are still dependent under the dome. You can't use temperature and pressure alone to pick the state. The same thing we've done for all other property values. So I'm going to kind of skip through this. We have a new chart that we can look at called the TS diagram. So we previously looked at TV diagrams or TP or PV diagrams, all three of those. But now we can look at TS diagrams, and it does provide us with some useful information, because at a glance we can see during a process maybe how much the entropy increases from one state to another as we go from point to point along that process. We'll look at some of these in more detail as we start talking about specific cycles and how they operate in terms of entropy. So let's do another example problem. In this case, we are going to look at a system. It's not necessarily a constant temperature system, but we're going to treat entropy as a property value, as it is a property value, and practice using the tables to look it up. So let's imagine that we have a rigid tank divided in two parts, equally in half. One part has a compressed liquid at 300 kilopascals and 60 Celsius. The other part is a vacuum. At some point, we remove that partition, and everything goes from one side to fill the entire chamber. So we want to determine the entropy change of the water during this process if the final pressure in the tank is 15 kilopascals. Okay, so we know the initial mass, the initial temperature and pressure. We don't know the volume, but we know it's half of the total volume, and we need to find the entropy change. Okay, so what type of system is this? Okay, it's a closed system. Is there any other details or information that can help us analyze it? Any other keywords in there? Rigid. Okay, so what does rigid tell us? Constant volume. Okay, so the volume changes from the initial state to the final state, but we know that it's just double whatever the total volume of that tank is. Okay, so let's look up some of these properties. So at 300 kilopascals and 60 Celsius, we actually have a compressed liquid, but we can say that S1 is equal to SF at the temperature. Okay, so for compressed liquids, again, we just use the saturated liquid state at that given temperature, not at the pressure, but at the temperature. So S1 is 0.8313 kilojoules per kilogram Kelvin. V1, specific volume, is VF at that given temperature, which is 0.001017 meters cubed per kilogram. Okay, so that's from table A4 in the back of the book. Okay, we don't know the total volume, but we know that V2 is equal to 2 times V1 because the mass remains constant, 1.5 kilograms on one side and 0 on the other, so the mass doesn't change. The specific volume of 2 is equal to 2 times the specific volume of 1. So if we wanted to calculate the specific volume at 2, it's 0.002034 meters cubed per kilogram. Okay, so now we know the specific volume at state 2 and the pressure at state 2 is given to us as 15 kilopascals. So we can use V2 and P2 to then look up the property values at the second state. So if we go to our tables, we find that it's from table A5, sorry, my writing is terrible. And we find that it's somewhere in between V sub F and V sub G on that table. So we need to calculate our quality. So the quality is equal to V2 minus V sub F over VG minus VF. So at 15 kilopascals, we're looking at V sub F, VG, and VF. Putting those into the equation, 0.002034 minus 0.001014 divided by 10.02 minus 0.001014. These are meters cubed per kilogram, which cancels out. But I'm writing it down because I always include my units. So we calculate X to be 1.018 times 10 to the minus 4 no units, it's unitless. Okay, so is this mostly liquid or mostly vapor? Okay, mostly liquid, it's very close to X equals 0. It's a small number, so it's mostly liquid. It's not totally liquid, some of it is vapor. So now we can calculate our entropy at state 2 is equal to S sub F plus X SFG. So again, we look up the properties, 0.7549 kilojoules per kilogram Kelvin, interesting units on entropy, plus X, which is our 1.018 times 10 to the minus 4, multiplied by S sub Fg is 7.2522 kilojoules per kilogram Kelvin. Okay, so S2 we calculate to be 0.7556 kilojoules per kilogram Kelvin. So delta S is just equal to our S at state 2 minus S at state 1. And we'll imagine that these are capital S's. So it's equal to the mass, 1.5 kilograms, multiplied by S2 minus S1, which is 0.7556 minus 0.8313 kilojoules per kilogram Kelvin. So we get negative 0.1136 kilojoules per Kelvin. Okay, so are we violating the increase of entropy principle?
Excellent.
Are we? So what are we calculating the entropy for? Okay, just for the system, right? Is it okay for the entropy of the system to decrease?
Yep.
Yes. If we were to calculate the entropy of the system and the surroundings, we would find it had to be a positive value. It's okay for this to happen, for the entropy of the system to decrease, but when we look at the surroundings, we should find a greater value than that. Okay, so if we wanted to calculate the entropy change of the surroundings, what would we need to know?
The surrounding temperature.
Okay, we would need to know the surrounding temperature, and then we could use our energy balance to calculate how much heat was lost during this process. Okay, there's no work interactions, so all we would have would be a heat transfer out of the system, and we would, heat transfer out of the system because our entropy is decreasing. So if heat transfers out, then we would have some heat transfer into the surroundings, and we could calculate that and determine the entropy generation. So this is the problem in ease. I'm not sure what, I did that a long time ago. I think the students have some problems to do with ease, but just of interest. If you don't use ease anymore, I don't know why not, because it's much easier to look up property values with ease than the tables, but you don't have to, just if you want to. Okay, so let's talk about the exam. Again, it's going to cover everything from chapters 1 through 6 plus today's lecture. However, the focus is going to be on material we've covered since the last exam. It's closed book, closed notes, and you get 2 sheets, front and back, of your own prepared notes. I've passed out this equation sheet. This is what will be used on the exam. So I've given it to you to help you study and become familiar with the equations. You can write on that and use it as one of your sheets or not. Any property tables will be given to you if you need them. I think one thing that tripped people up on the previous exam is they would try to do a problem and they realized they didn't have a property table for it the way that they were trying to do it, so they started assuming values. If you have to assume values, it means you're doing it wrong. Because I will either give you the table or I will give you the value or some chart where you can look up the value. If you're assuming values, then that's not the right way to solve those problems. Just a heads up on that. Concepts to know from before. So these are all the things that we've done up through chapter 5. You should be very familiar with doing all of these things already. If there are things that you struggle with, talk to another student, talk to me, make sure that you understand how to do these things. New things that we've talked about since last time were, the implications of the second law. What is the second law? What does it mean? How does it help us, or how is it useful to us? And then talking about energy reservoirs, heat engines, thermal efficiencies, the Kelvin, Planck, and Clausius statements, which are restatements of the second law, heat pumps, refrigerators, COP, reversibilities, Carnot cycle, and then today's topics, the entropy principles. So increase of entropy generation, and then entropy change of pure substances. So the problems that combine concepts from chapter 5, which is the steady flow devices, and chapter 6 are very good problems to expect on the exam. Okay, so we've done a few homework problems like that. We've done some homework, some problems like that in examples in the class. So these are some good examples, 56, 57, 110, of types of problems that I like to use on the exam. I'm not going to put these problems on the exam, but those kinds of problems. And then anything that requires you to have some knowledge of reversible versus irreversible cycles. I'm not going to ask you to do any of the proofs that were in the chapter. I think that doesn't test your understanding of the concepts very well, just your ability to memorize proofs. And then there will be at least one problem dealing with entropy. So when I say at least one problem, I mean one workout problem. And then there may be some like true or false questions or short answer problems that also deal with entropy. But at least one of the problems on the exam will deal with what we've talked about today. So if you're unclear on how to do isothermal entropy problems, looking up entropy in tables, calculating the entropy generation, I'd really focus on that and try to make sure you understand it. If you have questions, come talk to me. I don't expect you to fully understand how the Clausius inequality came about, or any grand analysis of complicated systems dealing with entropy. But I would expect you to be able to do some of the types of problems that we did in class today. Any questions? Don't worry, you will do great. You've done great all semester long. Keep up the good work. Keep studying. Don't change anything. So don't think that because you've done great before, you can stop studying. Keep up the good work, and we'll see you on Tuesday. And if everybody is here early,